everyone. I'm Rex from Menlo Research. We are a small open R&D lab and with a big ambition, building toward a general intelligence with that achieve real world impact through agents and robotics. Today I want to say about our story, a story of our really initial steps in teaching large language model to understand and reason about the world around us. This is a very first step to the final goal of building robots that can navigate complex environments and manipulate objects beyond the program actions. Okay, so who are we at Menlo? We are a fully remote team spread across continents, bringing together minds from all over the world. But it's not just from our core team, because everything we do is open source. So we also have the global community of contributors. These collaborators don't just share ideas, they actively help us to test, to build, and accelerate open source research. Okay, so we have built some practical tools. Some of you might know or might not know our work on local AI assistant like Jam.ai, and maybe you can see like Menlo API platform, and really relatively new branch is like research, and maybe you can randomly catch us on Reddit or maybe on X with Ichigo, local real-time voice AI, and really like it's like 3 months of research of the robotic branch, and we are also like currently actively experimenting everything, and all of those to answer the deeper research interest is that how do we bridge the gap between the cognitive power of AI and the physical capabilities of the robots. So our dream isn't just like make the robot that can follow our commands, but the robots that can truly understand the command in 3D space. Okay, so what are the current challenges? Traditionally, we can see that robotics spatial tasks involve complex pipelines. So we need to processing sensor data. We need to like build models and planning and make the planning paths. These can be powerful, but like often require significant engineering for specific tasks and environments, and maybe it can be brittle. So LMs, however, like it has so incredible ability in logical reasoning, planning, and also understanding language. So there is a possibility is that can we leverage these cognitive strengths of the LM to the spatial tasks? Like can even an LM that can like basically train on text only, the text data only, can learn and think in spatial. So this is require new findings, a way to like represent spatial information so that LM can understand it correctly. And another problem is that we all know that like data is always the big problem, right? So we have the way to like the real world data right now is not easy to scale. So we're trying to find another approach to scale the synthetic data so that we can use and train the model. So, and yeah, you can see by the way, this is from OpenSea 3D, really like wonderful work from the team. It's not our team, but like it's from another team, but we are building up on this. But we can see here, like not out there, not there are many open publicly dataset really good like this. They're really high quality data. So yeah. Okay, so before going up to the really complex problem like solving like finding the path, like reasoning over the room, we try to do a really small step to test out our hypothesis is that like can LM reasoning through the spatial. Yeah. So this is like the task is maze navigation. So this is really a simple, really, like it's just a toy task to test out. So the core idea of the model alpha maze is just like without any like vision adapter, the model could show the maze only given the symbolic representation. So we convert every maze grid and also words into the sequence of tokens, and it like and to see that the model like can we teach the model uh, to sequentially decision making based on these spatial rules. Yeah. And here is how we setting up the training data. So the maze is like 5 by 5 maze. It's really small maze, but we try to like to synthetically generate over like 500,000 of the different mazes, and also we divide our data set into multiple stages. Um, we create a straight success, which is like really is a straightforward that the start we can see here the start and the end is like just straight successful. But for the we have another one is the reset data, which is like we try to make the model go wrong path and let it call the function to restart the maze so it can try to know how it hits a dead end and it can start all over again. So yeah, and finally we have a small subset for reinforcement learning. We use the algorithm here is a GRPO. Like every other team, we just catch the new trend, so we use the GRPO to train the model. Okay, so is briefly how we convert the maze into the symbolic tokens. We can see like it's just like only like text tokens, and yeah. First of all, like we can see the supervised fine tuning. We all do this on the data set, and then after that after testing at stage 1 we saw that the model learn to solve the maze, but it's all generate sometimes it generates the suboptimal paths and maybe failure in some complex maze. So we try to test it on the stage 2, which is like the reinforcement learning. So yeah, and we design 2 functions, like 3 functions, but like mostly 2 of them is the most important. Is one is for the correctness of each solution, and another one is for the valid movement of the maze of the model in the maze. So this setup encourages not only the model reaching the final target, but it also doing but teach the model to do it efficiently. So we can see here how the model solve the maze. We can see like it choose the wrong path, but at that time it knows that it choose the wrong path, so it can reset the maze to rerun it again. And basically this model is only 1.5 billion parameters and like relatively small to test out on its task. Yeah. And yeah, with the testing like the alpha maze, we can prove that the principle of symbolic spatial reasoning. The real, but like as we all know that the real robot don't just like work on 2D space. We always work in 3D space. So we need to understand that the model need to understand that the concept of like maybe this is on top of something that the object is inside of something. So and maybe it needs to understand the precise coordinate of any objects. So this requires a more nuanced way to encode spatial information and reasoning about the object relationship. So we start another research called Alpha Space. This is like similar to the principle of the alpha maze, but this is converting everything to 3D space. So typically, this normally people will use the VOM to solve the task, but we are we are trying to like pushing the LLM like decoder only model to see if it can do the task. Yeah, and our approach is that we tokenize, like firstly we translate all the three scenes into the structure spectral tokens like SV form. So we break down the information into what is the shape and color of the cube, where is the object in the space, and lastly how high it is into the space. Yeah, this is a demo of like the training model. You can see like with the task of like picking the black cube on and place it on the green cube. And yeah, yeah, you can see sometimes it's like picking wrong things and placing wrong things, but like it is all like the model is reasoning through and trying itself. It's not like another like it's not another code or something. It's just like reasoning and reading through the results of the environment and trying itself. Yeah. Okay, so teaching this require a lot of examples. So and we don't know that like the data is really hard to get. So we are trying to generate synthetic data nearly like 300,000 of samples, and we create a virtual 100 by 100 grid table, and to have the LM reason about the location more easily, we divide it into 25 larger zones. So which we call this coast grid, and in each zone we divide into like four by four local grid. So to let the model precisely understand what is the coordinate of the object, and then we randomly like placing the object every else in this table to create synthetic data. And now what does the LM actually learn the output? For a typical task like picking and placing, a robot arm follows standard sequence of motions. Like it will approach to the object, and it will lower the arms, and then close the gripper and lift it up and move to another object, lower and release. So this is like mostly like 7 standard steps of like picking and placing an object. So this is basically similar to what humans do and when we want to pick anything. And lastly, for each of these 7 steps, the robot needs exact instruction. So we represent the instruction in a 7D vector to control the robot hands. You can see here the first is like the global coordinates of the object, and other is a local one, and the next one is like the height, and other is like for controlling the robot. And yeah, while promising that alpha space can like accurately picking and placing in a simulated environment, but how would it perform in the noisy and incomplete real world data? And we also observe that a composition task like stacking is more challenging than placing. So scaling this is highly like difficult. So we led us to think that maybe this is the upper boundary of large language model. So we led us to think alternatively and represent the information in 3D information. We represent 3D information in the better way, and potentially we will use the vision language model more directly. Okay, here is the next research of our team. We consider that we consider multiple way of common way they represent 3D data. Point cloud is like It's like they really common, but like it's simple, but it's really unstructured. So so after checking and choosing, we choose voxel. This is a 3D object or scene that can represent by voxel. Uh, like it's just like a single box into the 3D space. So why did this represent seem promising in our next step? Because of this is similar to 2D image. Voxel grids are really structured and regular, making it potential to represent uh, the image like we did before. And secondly, it can capture the volumic information, not just the surface of it. So here is how we represent our objects. This is like a chair in the voxel representation. The core idea behind this is like when we put the chair into the 3D space, we will slice it we will slice it like the medical image, like CT scan. So we slide every of the chair along with the z-axis. So we will have the 3D slices capture the information of all of the different depths of the chair. So why we need to do this? Why we don't just like put the 3D space into the VOM? Because of the current VOM, like Gemma or like QNVL, they are all trained on the 2D images and 2D videos. So our approach is that like we can flat the 3D space into the 2D space. And here is how we do it. First of all, we will take the 100 by 100 by 16 voxel grid and slide it along the z-axis. And this will give us 16 individual 2D images. Each of the image show the crossing section of the scene. And then we will like and each of the slides is 224 by 224 image, and all of them will be like 4 by 4. Why? This is why again, because of the lattice and the standard image representation of every VOM right now is 896 by 896. So that is our approach of how we can rescale and how we can make the data set like this. Yeah. So we can see here, like it was like when I proposed it with our team, like we all said that this is a crazy idea. Like it won't work in some, but luckily somehow our experiments show that this approach somehow work. The model can like identify what is the object in the 3D space. So yeah, but the key challenge here is that it will have information loss with this approach, and as well as it will reduce the performance of the model when we apply a really noisy and real-world 3D data. So we can see here, because of the voxel representation, prove that we can teach the VOM to understand 3D semantics by processing the sliding of the voxel data. So this is where we head into. We will like represent the whole room from 3D space, and we voxelize all of the objects in the room and create a similarly a data set of like multiple images into that room. And yeah, but like knowing that in the room isn't enough. Knowing what object in the room isn't enough, because we always, the final goal of us is that we want to create a robot that can use the voxelized representation of this and create reasoning to find the path. And yeah, and so with this VLM use is like 3D voxel understanding to reasoning about the navigation space. Yeah. So okay, so this is ongoing training project. We have some initial data, but the model sometimes we can see here the loss see in the information is really high. Sometimes the model will just like it worked really good in the simulation, but when coming to the real world, it will just like stumble into the real case, real objects. Yeah. So to wrap it up, our journey into the spatial reasoning with LMs cover like 3 big steps. First, with AlphaMaze, we show that like LM can like every LM right now can learn through 2D space rules through symbols and reinforcement learning. Then we have like the LM can like do 3D space and understanding 3D concepts from and reasoning from it. And finally, we can do like voxel representation that can use the current VLM 2D VLM to understand the 3D world using the voxel slicing for semantic understanding. So each of the steps will tackle the key piece of the puzzle and exploring a new way to represent the space and reasoning about it. Yeah. And the future is that, of course, a scene to real. These early results are exciting, but like the big challenges always remain is that like the scene to real gap, getting the models trained on a clean simulations to work in the real messy room like this is the next level of challenge. Looking ahead, like at Menlo, we want to make the system more interpretable and more trustworthy, so that we don't just want to just build a model out there, but we want to understand why the model choose to make that action, choose to create a plan to make the action for the robot. Yeah, and you can see here like our team invested in like several robot models to test the role. It is a really like beginning of us like starting a journey to testing out the robots. Okay, so thank you for the time and the attention. I'm happy to take any question and feel free to connect with me on my team.